Hello, today we will talk about how to do some MATLAB exercises related to previous lectures we had on basic statistics. So, as you may remember, we started by talking about how to visualize numbers. So let's start with doing exactly the same exercises as in this slides. So here I already put this sample data, and all this code which I will execute here is available online, so you don't have to type as I'm talking. You can just copy and paste relevant parts of the code to try it yourself. Okay, so if I click evaluate selection, then MATLAB is creating this age variable with 30 numbers. So those are this 30 numbers of student stress scale. And if we plot those numbers, we can see here is distribution of those numbers. That first subject reported stress level of 8, the last subject also reported stress level of 8, and so on. One thing when plotting data in MATLAB, it's important to notice is that MATLAB is automatically scaling plots between minimum and maximum on both axes. So, for example, points like here, which are maximum points or minimum points, or the last point, they can be placed right on the border. And if points will be used with smaller marker, it may not be well visible. So this is important point to note, that because sometimes when plotting data, extreme points may be not or may be overlooked because the way MATLAB plots it on the borders. Okay, so still looking at this plot is more visually appealing than just looking at these raw numbers, but nevertheless it is still difficult to make sense out of those numbers. One way to somehow improve it is to plot sorted numbers. So it is exactly the same plots, but here I display this data sorted by value of stress. So one person responded that it has 0 stress level, one person 1, and the most people, now it is obvious that most people reported stress level of 7. So exactly it is the same data, just now instead of sorting it by putting in this arbitrary order by which people were interviewed, rather I sorted the responses, and now it's easier to see if there is any clustering in data. But again, the even better way is to plot a histogram, and here you see this histogram with bin 1. So it is a little bit jumpy, so maybe better option it would be to choose histogram with bigger bin. And here you see that this is data plotted from exactly the same data, just here I was using bigger bin, so here I was using step size 3. So in this histogram function, here I can specify what are the minimum value, maximum value, and what is the step size. So with this step size of 3, I'm putting together scores of 1, 2, and 3, 4, 5, 6 together, and so on. And here you see that distribution looks much smoother. But some small details can be lost. So if, for example, this type of fluctuation here it is noised, then having this bigger bin is smoothing it and getting rid of this noisy fluctuation. But also note that here it is this nice build-up of this value, of this peak, that values are consistently increasing and later systematically decreasing. But here with this bigger bin, we don't see it, we just see this one bigger peak, which may be sometimes better to display data in this way, but sometimes this type of data could be more convincing that this is a real change in tendency and not just one outlier point. Okay, so we also spoke about normal distribution, and the way to generate normal distribution is by using function rand_n. So here it is generating 10,000 random numbers. So let's see those numbers. Those numbers have mean 0 and unit standard deviation of 1. So you can see that most of those points, of those 10,000 points, are distributed around 0, with very few exceeding 3 or being smaller than -3. And again, even a better way to do it is to plot data displaying this histogram, and now you can see that this data is distributed in this normal way with mean 0. Here in histogram I didn't specify what is the step size. Here I just put 20, which means I want to divide this histogram in 20 equal intervals. So now MATLAB automatically takes the minimum value and maximum value of this g and divides it in 20 equal intervals. So this is important to keep in mind, because it means that this interval around 0, it probably is not centered right exactly around 0, because probably by chance there was slightly bigger positive value than negative. So if it is distributed, divided in equal intervals, then this bin will be slightly shifted and will not be exactly centered at 0. So when looking at data, it's always good to calculate some basic description of this data. So for example, mean, standard deviation, and median. And what you can see is that the mean is very close to 0, the standard deviation is very close to 1 as we expect, and the median is again close to 0 as expected. Probably if I would generate not 10,000 but 10 millions of points, those values would be much closer to 0, 1, and 0. One thing to keep in mind is that it's always good to plot to calculate mean and median, because if mean and median are quite different, it means that we probably have some outliers in our data. So for Gaussian symmetric distributions, mean and median should be very close to each other, as in this case. But because mean is much more affected by outliers, if there are some significant outliers, we will see that mean and median are quite different. So this is a good sanity check, quality check of data. If we have large data sets and we cannot visually examine everything, then by comparing those two numbers could be useful. Okay, so now you can pause and have some exercise. So now let's think how to generate some bimodal distributions, not unimodal as Gaussian distribution, but rather bimodal distributions. So as you remember, bimodal distributions were, for example, like here. So let's think how to modify MATLAB code to generate such bimodal distribution. So please pause for a time unit and do this simple exercise. Okay, so I assume that you did this exercise of creating bimodal distribution, and here is some example how it is possible to done. So instead of generating of one Gaussian, we can generate two Gaussians, and here I'm generating with this unit standard deviation and 0 mean. So I'm not changing those values by multiplying by 1 and 0. But the second Gaussian, now it will have a wider distribution and it will be shifted by 5. So let's plot the data. So this is, now I plotted in two different colors data generated with this G and R variables. So here you see this original Gaussian with 0 mean and unit standard deviation. Here it is Gaussian with twice bigger standard deviation and shifted by 5. The mean shifted by 5. So you see that those points are a little bit overlapping, but they are largely in different regions. So how to plot a histogram? Well, I can create new variable where I will connect G and R, and now this will create this bimodal distribution reflecting this data. Okay, so again you can now pause and so now will be another exercise, and here let's think how to create some simple skewed distributions. So we were talking that not all distributions are symmetric. Some distributions can be skewed in different ways. So let's think how to generate some simple skewed distribution. Please pause and unpause after you create such distribution. Okay, so here is some example how to create such skewed distribution. So in this case, I again create some Gaussian distribution, but to the end of this distribution, I will attach some uniform distribution. So here you notice is rand without n, so it will generate a uniform distribution. So let's see how it look like. So it is basically I generate Gaussian and I also generate data which is uniformly distributed, and now if I add concatenate both variables together, those two vectors together, it will create a set of numbers which is if you look at the total distribution, it will be skewed. And here is another exercise. Please think how to create skew distributions in different ways, and there is infinite number of ways. So let's think about 2-3 other ways in which you can create skewed distribution. Please pause. Okay, so if you successfully created some other skewed distributions, let's see how what are the other possibilities which I created. And those exercises may not be directly related to helping you improve your statistics skills, but those exercises are also designed to help you get more familiar with MATLAB. So you can, by thinking how to create distributions, you can get more proficient in generating some artificial data, and later when you are analyzing your data, sometimes it's really good to compare it to some generated data. And if you are familiar with different ways how to generate some data, it may be quite useful. Okay, so here one way to generate data is just take this Gaussian distribution and just square it. So here is example how it look like. So small numbers squared, it will be still small, 1, it will be 1, and for some few values which will be above 1, they will be skewed, they will be proportionally increasing, quadratically increasing. So you will get this highly skewed distribution. But what we can do is we're also talking that because in many statistics we want to work with normally distributed data, and one way to get around it is to apply some unskewing procedure. So in this case, just applying this square of this data, it will help to reduce this. So let's see on the original distribution. This is after unskewing, and we can again repeat this process of taking square root of this data, and now you can see that this distribution is much more symmetric and can be considered as a quite good approximation of normal distribution. So you see, here is original distributions, here I take square of it, here I took square of this second distribution. So again, as I mentioned before, making such transforms of data and calculating final statistics on this transform data is something acceptable by vast majority of statisticians. The one thing to remember is that if you are doing this transformations to one set of data, you have to do it the same transformations to all sets of data which you are comparing. Another way to calculate to make some skew distribution is again just by taking random distributions and only taking absolute values, so only positive values, so converting negative values to positive values. This is what this function ABS absolute value will do. And to unskew it, we can try it either we can try it by taking the square root, or as we mentioned, we can also try to do it by inverse by 1 over the original values. So let's see how it works. So this is unskewing with square root. This is by taking this inverse 1 over g, and this is original distribution. So again, if our original distribution is quite skewed and we don't want to apply some non-parametric statistics, we can always try to convert it to more symmetric distribution. And in this case, this square root was working better. And there could be many other ways to unskew data, and you can design even own functions to do unskewing, but again, it has to be consistent across all data sets. Another way to generate some this skew distribution is, for example, by deleting all the numbers which generating normal distribution as before, and here we are just deleting all values smaller than 0. And if we, for example, plot negative of this, then we will have distribution skewed in other direction. MATLAB also offers distributions with different probability distribution functions. So, for example, there is Pearson distribution, and we can generate it. So this distribution is by design skewed. So instead of doing ourselves some skew functions, skew distributions to generate some data, we can use some already built-in MATLAB functions to generate such distributions to compare to our data. Okay, so the last exercise for this part, it will be to generate uniform distribution. So as you remember, example of uniform distribution, it was for example here, where it was number of students across different grade levels. So in every grade there is more or less the same number of students, so this distribution is approximately rectangular. So how to generate such distribution? Please pause and do this exercise. Okay, so assuming that you did this exercise, here is the answer. So we in few lines above use this function. It is function rand, which generate this uniform distribution. And here we can see that for 2000 numbers and binning them in 10 categories, we can get this more or less uniform distribution. Okay, so we also spoke about z-scores. So we will use the same data as on the beginning of this class, this fictional stress scores of 30 students, and we will calculate what is the mean standard deviation of those distribution. And as you remember, the z-score, it is taking from each value, subtract mean from entire data set and divide by standard deviation. So here it is how to do it in MATLAB, that we calculate mean of this vector, we calculate standard deviation, and now from each value of this vector h, we will subtract mean and divide by standard deviation. So here it is. So in blue, I plotted original data. In red, I plotted z-transform data. So as you see, all the relations between points are preserved. So this is higher than this, exactly as here. This point is the same value as the last point, so it is exactly the same here. Just after the z-score transformation, all values are now around 0, and they have this standard deviation of 1, so they are fluctuating with given variability around 0. In MATLAB, we don't have to do this simple calculations ourselves. There is built-in function z-score, which will do it for us. It will transform data in z-score and calculate what is the mean and standard deviation. So I can now apply these functions and plot it on the top of this. So now those those black stars on the top of the red curve are this points from this MATLAB z-score function. So as you see, the values are exactly the same if I calculate it by hand or if I use this built-in matlab function. We also spoke that how to convert any data from z-scores back to original data. So we were saying that it can be done by multiplying the z-scores by standard deviations and adding mean. So here it is exactly 2 lines doing exactly that. So the first line is doing this conversion and second is just plotting. So here what I'm plotting in blue is original data and as a red stars are data converted back from z-score. So as you see, we can exactly recover what were the original values after this going back from z transform. We also spoke about effect size in last lectures. So just to remind you, this effect size was here in slide 36. So if you have two populations with same standard deviation and you would like to get some intuitive measure how different are those populations, then you can just look at the difference of means divided by standard deviation. So we can easily do it in MATLAB. So here I will clean all the previous variables and I will calculate two normal distributions. And as you notice, here I'm multiplying by 4. So now I will generate normal distributions with standard deviation of 4, so they will be wider than usual, and the second distributions will be shifted by 2. So here I'm adding 2 to those values, so I'm shifting mean by 2. So let's see how those two distributions look like. So if I plot original data, you see that this red and blue points for R1 and R2 data sets are overlapping quite a bit, so it would be difficult to see if there is some statistical difference between those two distributions just by eye. But if I plot histogram, then it's a little bit easier to see that this is the first distribution, second distribution, and here we can see that consistently this one distribution is more shifted to the left and other more to the right. And we can calculate mean of both distributions, and D, it is effect size. So here in this case the effect size was 0.5. So as we remember, it is considered quite significant effect size. So if we have some population and we apply some, if we have two populations which are different by, which are quite overlapping, but the effect size is this 0.5, usually it is considered quite significant effect size. And we had here some rule of thumbs that effect size of 0.2 is considered small. This what we had, it was medium, not large, and the large is around 0.8. Okay, so now we will do some statistics. So we will test if average height of basketball players is significantly different from a general population. So here we will generate some artificial data. Here we will have generate data of height, and it will be 100 numbers. So we will again use this rand n as a convenient method to generate this random data. So it will be normal distribution. The variation, it will be 10, and we will add 175 to the mean. So our height distribution will be centered around at 175 centimeters. So let's see how this data look like. So here you see this 100 people. Each of those blue dots is showing height of one person in our population. If we plot a histogram, then we see that as designed, the distribution is centered around 175, and it is approximately normal distribution. Now what we will do is that we will also generate some other fictional populations, so it will be height of basketball players. So here we'll have 10 basketball players, and we would like to test if the height of those basketball players is significantly different from these general populations which we generate here in variable in this vector h. So here we can plot those two distributions. So here what you see is this original blue distributions, and here in green is distribution of heights of our basketball players here in green. So as you see, it is more to the right of the original distribution. So it seems like basketball players are higher than, taller than general population, but how to test it? Here note that it's not very convenient to plot, it's not very easy in MATLAB to plot two different histograms on top of each other with different colors. So here I use some a little bit trick. So for the second distribution, I had to define face color as those red, green, and blue values, this vector of 3, and I have to use this comment find object, where I was taking get current object, so it was this histogram. So it is a little bit convoluted way to plot it, but you don't need to know the details how it works. You can just if you need it, just take this code as a template, and by modifying those 3 values, and those values have to be between 0 and 1, you can send the face of color of the second histogram to any color you wish. And so we had this 2 different histograms, and the way to test it in MATLAB is to apply this t-test 2. So this t-test 2, it takes 2 distributions, and those distributions can have those 2 vectors can have different length. As in our case, we had 100 people in original distributions and only 10 people, 10 basketball players. And if we run it, then it will give us first value. It will be if this hypothesis is true, that those distributions are different, and the value is 1. And here you have p-value, that it is p 1.27 and so on, to minus 4 to 10 multiplied by 10 to minus 4. So it is 0.0001. So it is very small p-value, so it is highly significant difference in heights between this basketball players and general population. Okay, but in last lectures we spent a considerable amount of time trying to get intuition behind t-test, and by doing t-test by hand. So let's do exercise doing exactly that. So here is some code how to do this t-test by hand. So here what we will do is that from this distribution, from this 100 people in general population, we will choose by random 10 people, and we will calculate what is the average height of those 10 people, and we will repeat it 100 times. So here this line, it is just selecting some 10 random numbers. So here it is 10 random numbers with value between 0 and 1, and if we multiply it by length of age by 100, then those numbers will be now between 0 and 100, and the silly comment will just change those numbers to integers. So if we run this loop, now we will get this 100 values of mean for different subsets, and now we can plot the distribution of those means. And let's plot what was the original distribution. So here you see that original distribution was changing between around 150 to 200 centimeters. Now this our distribution, if we it is changing from 165, so from around this to around 185, so it is now much narrower distribution. What it means is it shows how likely it is by chance to get 10 people and to have the average height to be around let's say 180 or 175. So what this plot is showing is that it is quite unlikely, for example, to take subset of 10 people from this original population and have this height bigger than, let's say, 185. So nobody, no random sample of those 10 people had it. So let's compare how was the mean of our basketball players. So the mean of basketball players, so this is mean of B in this vector B. It was defined, it was 188 centimeters. So it means that it is very unlikely just by chance to take 10 random people from our population and have the average height as high as the average height of those 10 basketball players. So now comparing the value of this basketball players to this distribution, it gives us idea that really it seems like those basketball players are significantly taller than general population. And how to quantify it? Well, we can convert it to z-scores. So now if we look what was the difference between those two vectors divided by standard deviation, what was the original distribution, it means that the basketball players, they have the average height of basketball players is at z-score of 3.8. So it is more than 3.8 standard deviations above the mean. so very few values are above this point. So how to get some estimate, for example, of p-value from that? We can use a function of norm cumulative distribution function of normal distribution to get this approximation. So these functions will, assuming that this is, here we calculate in this line what are the z-scores of z-score of this average height, and now we can see how likely to have each such z-score. So here, let's see how likely it is to have z-score of 0. So here you see the answer is 0.5. So if we have normal distributions with, as for z-scores with mean 0 and unit standard deviation, 50% of scores will be below 0. If we have z-score of 2, then 97% of points will be below z-score of 2. So z-score of 2, it will be probably somewhere here. So if it's average, it will be somewhere here. So 97% of points will be on the left, will be smaller than this. And here, let's test what will be the likelihood, what will be the percentage of points smaller than this z-score we observe. So it shows that 99.99% of scores will be lower than this z-score of 3.8. So it shows that p-value for this t-test, it would be very similar to what we obtained with doing this t-test with this t-test function. So it would be 0.0001, so it will be at this level of 10 to minus 4. So both doing by hand and doing this by t-test function return the same results. So again, take a closer look at this code to get some better intuitive understanding how we calculate this. So here we can say that p-value is equal to 1 minus this. So